Hello and welcome to helpyourmath.com. In this video, we're going to look at examples of graphing exponential functions. And it's important to keep a few things in mind. For all exponential parent functions, so these would be of the form f of x is equal to a to the x, all of these, whether it's exponential growth or exponential decay, have what I refer to as a critical point. And that critical point for the parent functions is always at 0, 1, right? Because if you plug in 0 for x, a to the power of 0, any positive number raised to the power of 0 will be 1. And when we're talking about exponential functions, we're only talking about positive bases. So a to the 0 will equal 1 no matter what. So I refer to this as my critical point. I like finding the critical point to kind of help me as a guide of kind of where the graph kind of flattens out versus where it increases or decreases very dramatically. So look for the critical point, and what we do is we look for the critical point because exponential functions are functions. So these would have all of the same characteristics as transformations of other functions. So for example, oh, I can't use a, can I? We'll say, we'll just use f times a to the x minus h plus k. This would be just like any other function. So this tells us two things. If it's positive or negative, it tells us whether it's going to be facing up or facing down. If it's bigger than 1 or smaller than 1, that tells us if there's a stretch or a shrink. And then any transformation, if there's something happening within the exponent, that's going to move our exponential function h units to the left or right. And if there's something being added to the function, that's going to move it up or down k units, depending on whether it's positive or negative, just like with every other function. So this should be nothing new. H comma k that I just wrote there, no, actually h comma k is nothing. H comma k plus 1 will tell us where our new critical point will be. So this is going to identify where the new critical point is. It will be found at h comma k plus 1. And why is it plus 1? Because the original critical point was at 0, 1, so we're already starting 1 up. We would add 1 from there. If f happens to be negative, that can affect the critical point, but we'll see what happens when we see a negative. In each example, we want to find the domain, the intercepts, the horizontal asymptote, and the critical point, and then we're going to sketch a graph. So our first function, we have f of x equals 2 to the x plus 5 plus 3. I recognize that this is exponential growth because my base is 2, so this is a base 2 exponential model, indicating that it's growth. The domain for any exponential model will be all reals. There's no restrictions on the domain, so it's going to be from negative infinity to infinity. Before I identify the x and y intercept, I like to identify the critical point. So remember, on the parent function, the critical point is at 0, 1, and the critical point on our transform function will be h comma k plus 1. So let's see what that is. In this case, h, so remember what it is, it's x minus h, but we have x plus 5. So how do we interpret that? Well, that means that there was a negative 5, right? Because that would be x minus negative would give us that positive. And then k is 3. 3 plus 1 is 4. So we have a critical point at negative 5, 4. So that's where we originally, that's where that change from kind of flattening out to going really, really steep will occur. I'm going to go ahead and graph that point because that's going to kind of help me here. So here it is right here, my critical point. Now, the graph, remember, this is growth, so it's going to look like this. This kind of indicates to me that we are not going to see a x-intercept. And we can verify that because we can say, okay, well, to find an x-intercept, we would plug in 0 for f of x. So we'd have 0 equals 2 to the x plus 5 plus 3. Then we would subtract 3 from both sides. We get negative 3 is equal to 2 to the x plus 5. So what this is saying is, what power would I need to raise 2 to in order for the result to be negative 3? If you raise 2 to any power, it's always going to be non-negative. It's never going to be 0, and it's never going to be anything negative. So this doesn't make any sense. That's a contradiction. There is no x-intercept, so we're just going to say none. There will, however, be a y-intercept. Let's see if we can figure that out. So to figure out the y-intercept, we plug in 0 for x. That's going to be f of 0, 2 to the 0 plus 5, that thing plus 3. So this is 2 to the 5th. 2 to the 5th is 32, and 32 plus 3 is 35. So we do have a y-intercept. It's definitely not going to appear on my graph. It's going to be at 0, 35. The horizontal asymptote. So how do we find the horizontal asymptote? We figure that out. That's a horizontal line, so that's y equals, and what does y equal? Y actually equals k. So we do get to use this without having to add 1. So our horizontal asymptote will be y equals 3. We can go ahead and draw that in. And if you want to get more precise, you can make a table of values to kind of help you. I would suggest 2 points to the left of the critical point and 2 points to the right. If you want to just wing it, that's fine too. And we can't use the horizontal, the y-intercept, unfortunately. If we do choose to plug in points, we have x and f of x. So our critical point is at -5. So what if we look at -7, -6, -4, and -3? -7, that would be 2 to the, I don't know what I'm doing right there. Let's scoot over. 2 to the -7 plus 5, and then that thing plus 3. So -7 plus 2 is -2. 2 to the -2 is 1 over 2 squared. That's going to be 1/4 plus 3. So I end up with 3 1/4. When I plug in -6, 2 to the -6 plus 5, and that thing plus 3. This right here is -1. 2 to the -1, that's the reciprocal of 2. So that would be 1/2 plus 3, which will be 3 1/2. And that's what we expect. We expected these as they get smaller and smaller to get closer and closer to 3, which they are, because -7, 3 1/4 is closer to 3 than 3 1/2 is. So it'd start out like that. If we plug in -4 next, I'm running out of space here. I'm going to go all the way down here. 2 to the -4 plus 5, and that thing plus 3. Well, -4 plus 5 is 1. 2 to the 1 plus 3, that's 2 plus 3 is 5. And last but not least, -3, 2 to the -3 plus 5 plus 3. -3 plus 5 is 2. 2 squared is 4, and 4 plus 3 is 7. So we have -4, where am I? -4, 5 right here. And then -3, 7 up here. So we have a nice smooth curve, and it kind of looks like that. So you can see it's getting flatter towards the left, and it shoots way up toward the right. We're expecting that to cross the y-axis at 35. The actual drawing, I was pretty close on that. That's what it looks like when I did it on a more accurate device. Okay, for our next example, here's where we see some weird things going on. Okay, first let's figure out what our critical point is, because we know I like to do that. So the critical point, well actually, wait a minute. We have a negative here, so that's kind of throw things off. What's that negative going to do? That's actually going to reflect it over the x-axis. So when we have that reflection, instead of the critical point being at 0, 1, it's going to move the critical point down to 0, -1. Okay, so then we're going to use that as our guide to help us. So we have h is going to be 1. So this is going to stay 1, and then there's nothing over here, right? That's like plus 0. So this would end up being -1, because it would be -1 plus 0. But we do have to be careful with that critical point with the negative. So the negative in front of the base is going to flip it over the x-axis. It's going to turn our critical point negative. Okay, so now we know our critical point is at 1, -1. Now we can do the domain. Domain is all real numbers. The x-intercept, are we going to have an x-intercept? Well, let's see. If we have 0 equals -4 to the x minus 1, well, can we raise 4 to a power and the result is 0? No, we can't. So there's no x-intercept. Okay. Y-intercept, we would plug in 0 for x. So we would say f of 0 is equal to -0 minus 1. That would be -4 to the -1. This is the reciprocal of 4. We end up with -1/4. So we do have a y-intercept at 0, -1/4. Our horizontal asymptote that's found at k, this is going to be y equals k. In this case, k is 0. Okay, so now we have some information. We can graph our horizontal asymptote at 0. We can graph our critical point at 1, -1, over 1, down 1. And now we might want a little bit more information about this graph. So I would suggest choosing points around 1 to help us as a guide. So we have x and f of x. I would choose -1, 0, 2, and 3. Just nice numbers that are kind of close by, especially with a base of 4. These numbers are going to get huge fast. Or in this case, small fast, since we're negating everything. Okay, when we plug in -1, we get -4 to the -1 minus 1. This is -2. 4 to the -2 is 1 over 4 squared, and there's that negative in front. So this is going to end up being negative 1 over 16. So here we get negative 1 over 16, really, really close to 0, but not quite there, right? It's never going to actually reach 0. If we plug in 0 for x, we get negative 4 to the 0 minus 1. That's negative 4 to the negative 1. This is the reciprocal, the negative reciprocal of 4. That's going to be negative 1/4. If I plug in 2, so f of 2, that's going to be negative 4 to the 2 minus 1. 2 minus 1 is 1, and that's just going to be negative 4. And last but not least, if I plug in 3, when I plug in 3, oh look, and those match, which they should have done. That's good. If I plug in 3, I get negative 4 to the 3 minus 1. 3 minus 1 is 2. 4 squared is 16, and then we negate that, so it's negative 16. So that one's not even going to be on the graph. Okay, so let's see. We have negative 1, negative 1/16, so really, really close, but not quite there. Negative 0 and negative 1/4 will be like right there. Negative 2, negative 4 is down here. And then we're all the way off the graph, you know, like down here somewhere. So this graph really close to 0, and then it goes way far down. So it should look something like that. The computer, oh look, it's like perfect. Nice, go me. Okay, and in our last example, we want to do all the same things, but now we have a different function. And I noticed something different about this function. The base this time is a fraction between 0 and 1. So when the base is something bigger than 1, that's exponential growth, which is what we've seen, well, except for the negative. But exponential growth, it's like flat and then it shoots up towards the right. With exponential decay, it does the exact opposite. It flips over that y-axis. So it's really tall in the negatives, and then it kind of flattens out in the positives, right? Because you're taking a fraction, and if you take a fraction and you keep multiplying it to itself, it gets smaller, and the value gets smaller and smaller and smaller. So with decay, we are going to see our graph kind of flip around. Okay, we know me, I like to figure out the critical point. So the critical point, remember for the parent function, it's at 0, 1. So how does it move for our f of x here? For our f of x, it should be x minus h, so that would be minus 3. And then it's going to be 4 units down from 1, so that would be minus 3. So our critical point is at negative 3, negative 3. Let's go ahead and graph that critical point. There it is. Okay, and let's figure out the rest of the details here. The domain of this exponential model is all real numbers, negative infinity to infinity. The x-intercept, so moment of truth, does this graph have an x-intercept? If we plug in 0 for f of x to figure out the x-intercept, we end up with 1/2 to the x plus 3 minus 4. Add 4 to both sides, we get 4 equals 1/2 to the x plus 3. So is it possible? Yes, it is, because it's equal to something positive. That means that an x-intercept does exist. Now, I'm going to go through how we can figure it out. If you haven't done this in class yet, that's okay. Just bear with me for this little bit. But we're going to use what's called the one-to-one property. And what that means is we're going to use something that says if we have x to the a is equal to x to the b, which we have now, well, we don't have now, but we do have something equals something, then what that means is that a must equal b. So if we can write 4.5 as the same base, then we can set the exponents equal to each other. So 4.5, can you think of something that they're both powers of? They are both powers of 2. So 4, I'm going to rewrite as 2 squared, and 1/2 is 2 to the negative 1, right? So I just rewrote, this is still equal to 4, and this is still equal to 1/2, but I rewrote it, I don't know why I put a negative there, that was weird, but I rewrote it so that way they have the same base, and then this is still to the x plus 3, so we can't change that, but we can rewrite each of the bases. Now what we have over here, we have power to a power. So do you remember how to simplify power to a power? We multiply the powers. So this is 2 squared, this is going to be 2 to the negative 1 times x plus 3, distribute the negative, and we get negative x minus 3. Now that we have the same base, right, they're both base 2, since they're equal to each other, that means that the exponents must also equal each other. So that means that 2 must equal negative x minus 3. I'm going to add x to both sides just to turn it positive, and I'm going to subtract 2 from both sides. Add x, subtract 2, and then I end up with x equals negative 5, a nice real integer. Hooray, we have an x-intercept. That x-intercept is at negative 5, 0. Whoa, negative 5, 0, and that's going to help us. That's one more point that we actually can use. How about the y-intercept? So to figure out the y-intercept, we're going to plug in 0 for x. So this is going to be, I'm just going to come over here, f of 0 is 1/2 to the 0 plus 3 minus 4. This is 1/2 to the third. 1/2 to the third is 1/2 times 1/2 times 1/2, which is 1/8. Here's where the math gets a little bit tricky. 1/8 minus 4 is going to be, that's 1/8 before -4, which will be -3 and 7/8. Oh, I forgot to put the 0 though. 0, comma. So we do have a y-intercept. It's not as nice as the x-intercept, but it does exist. It's at -3 and 7/8 here. So you can kind of see the graph taking shape. Remember how it's supposed to be going up tall and then it comes down low and flattens? That's what we're seeing already even with these 3 points. The horizontal asymptote on this graph, remember what that is? That's y equals k, and in this case k is -4. So that point, that y-intercept was like right on -4, but it's actually not. It's just slightly above, and this graph will always remain above -4. If you want to do 2 more points, since we already have 3 points, we only need 2 more. If you feel comfortable with these 3 points, you can probably just connect those with a nice smooth curve. I'll plug in -4 and -2. If I plug in -4, f of -4, that would be 1/2 to the -4 plus 3 minus 4. -4 plus 3 is -1. This means this is 1/2 to the -1. That's the reciprocal of a half, which is 2. And 2 minus 4 is -2. So we have a point at -4, -2. Perfect, right in line. And then if I plug in -2, I'm running out of space here, f of -2 is equal to 1/2 to the -2 plus 3 minus 4. -2 plus 3 is 1, so this is 1/2 to the 1 is a half minus 4. So what's a half in front of -4? That is -3.5. So -2 is -3.5. Whoops, exactly where it should be. Connect these with a nice smooth curve where it's coming up tall in the negatives, and then it kind of flattens out as we get to more positive. And there's what the actual graph looks like. I did pretty good that time. These have been examples of graphing exponential models. Thank you for stopping by.